Okay, let's look at this graph. This function y equals sine x over x. Okay, clear that function out and then put in sine x over x, and you can look at that as well. Make sure you're on radian mode. Okay, make sure it's on radian mode. I think I'm just going to go back to what we'll just look at one side of it here. I'm going to go for 0 to 4.7 for now. But we really only need about negative 0.5 up to 1.5 for this function. There's the right side of that function. If you go farther out to the right here, what's going to happen with this function? It goes back up again. Remember though, what happens? You're dividing something that. What happens with this value here? Sine fluctuates between 1 and negative 1. This keeps getting bigger and bigger. So you're doing something that fluctuates between 1 and negative 1 divided by something that's bigger and bigger all the time. So what happens to the overall values as time goes by? Yeah, they get smaller and smaller. They kind of fluctuate up and down, but overall they're going to get smaller and smaller. So if you made this go now to a bigger number instead of 4.7, 10, you can see a little bit more of it. And I know that you probably graph it on the other thing. Okay, it just kind of trails off at the bottom there. What can you say about that function? It has a limit as x approaches infinity. Does it have a limit? No, it doesn't, or yes, it does? It does, right? What's happening with the values as you go farther and farther there? They get closer to 0. Absolutely. They get closer to 0. It doesn't matter that it's hovering above and below the thing. As you go farther this way, they get closer and closer to 0.
Does it ever equal 0?
It's the same as the other as the one we just looked at, right? This never equals 0, even though it looks like it on the calculator. This actually does equal 0 because it crosses back and forth, right? It actually equals that value at every time it crosses the axis. It's never going to become a straight line like that, though, if that's what you're asking. Like, it's going to keep hovering like that, but you still say that the limit is 0. Okay? The limit as... It looks like from the graph that the limit as x approaches infinity of f of x is 0. It does still have a horizontal asymptote. Y equals 0 is still a horizontal asymptote, even though the graph touches it, right? Even though the graph crosses it. In grade 11, you wouldn't probably call that a horizontal asymptote. That doesn't fit what we normally talk about in grade 11, even though it is. Okay, since this is true, we can see that if we want to prove that this is true, it's hard to see what's happening with this. The previous function, the 1 over x that we looked at before, 1 over x, you can pretty quickly rationalize that is going to be, that's going to have a limit of 0 as you make x bigger and bigger. Since it's just one value over another here, how can you tell pretty quickly that this is going to have a limit here of 0, 1 over x? If you kind of think about, you can't really substitute in infinity, but you can think about what's going to happen if I was to do this, 1 over infinity, 1 over a bigger and bigger number. What happens with that? 1 divided by bigger and bigger number. Okay, closer and closer to 0, right? if you did it the other way, 1 over negative infinity, right? It's still going to be same thing going to happen, right? This one's harder because it's harder to think about this. I think I alluded to it before. This one, if you have sine x over x, it's harder to think about what happens as those two, as x gets bigger here. On the bottom, as x approaches infinity, like sine of infinity over infinity, this is harder to think about. What does that equal to? Infinity, I mean, this x on the bottom gets bigger and bigger. The value on top fluctuates, right? So you have a number fluctuating between 0 and 1 over infinity. What you can do is this, they call it, I don't know what they call it in the textbook, one of these two things. The sandwich theorem or the squeeze theorem. If you want to prove something, like you can see from the graph, it's going to trail off to 0 here. But if you want to prove something or confirm it, you can't just say, oh, look at the graph. The graph isn't a proof of anything. But what you can do is you can pin it in between two functions where it's really easy to see what the limit is. So we're going to pin this in between two functions here. So what this sandwich theorem means is pin this function between two others, or squeeze it in between two others. Okay, two others that have the same limit. All right. Let's use this instead. How far back do I have to go to get to my axes here? Back to the way they were. Okay, so let's put in here instead sine x over x. You can do it on your calculator and then graph these other two functions as well. Okay, so we want y equals sine x divided by x. And we'll look at just one side of it because we don't really need to look at the rest of it.